Alright, at this point you should have at least talked through with your partner what you think is going to happen in situations A through D. For the first one, it is saying that the masses are the same. So if I have this frictionless pulley and I hang a mass of whatever mass, doesn't matter, on either side that is of equal masses, we're wondering what would happen. So I've got this little pulley and I have equal masses right here. Oftentimes what I see people do is they think that the lower one is going to accelerate, so let's do that. If I have M2 equal masses like this, nothing happens. If I have them right here, nothing happens. If I put them at the same height, nothing happens. It's not about where it's placed, it's about the forces. These two have the same force because in this case, right, it's the force of gravity, and if they have the same mass, they're going to have the same force of gravity. So here, right, nothing is going to happen. There's going to be no acceleration, so nothing. There's going to be no acceleration because the forces are going to be balanced. And we'll be drawing the free body diagrams for these in a minute, but if they're the same mass, then they'll be equal forces. Part B says M2 has a slightly larger mass, so now I'm going to replace this so that M2 is a larger mass, but not a whole lot larger. Give me a second. When you were making your predictions, you should have hopefully said that it will move here, not just move, but will accelerate. You should have talked about the direction that M will accelerate and the direction that M1 and direction of M2. So here, I've got my M2 on the right. It's a slightly larger mass than M1, and what happens when I let go is it starts to accelerate up. So I'm going to show it down here so you can see a little more dramatically. So you'll notice not only is it moving, it starts slow and then it starts to accelerate at the as it moves up as time goes on. So here we're going to have an acceleration in two directions. So M2 is going to be accelerating down. So M2 accelerates down, and M1 starts to accelerate up. Remember, it's not just about the motion, it's not the velocity that I care about so much, it's the direction of the acceleration. Part C, it says M2 has a much larger mass, so instead of them being just slightly different, I'm going to change it so that M1 is much, much smaller mass. Hopefully you are guessing that the direction of acceleration is going to be the same, but there is going to be something different. So here, much greater mass, much smaller mass. Oops, that fell off the pulley. All right. Ooh. So here, still the same idea. The M2 accelerates down, the M1 accelerates up. But now you should notice that that is accelerating at a much faster rate. You've got, oh, that fell off the pulley. You saw it the first time. You can rewind if you didn't see it. Here, so it's going to be the same thing here, but with a greater acceleration. Part D, it says that M2 still has the same mass, but now there is no M1. So if you were to take this off, now this is just M2 hanging by itself. There's nothing holding it back, so see how M2 would just fall? So for that, I read as if there wasn't a pulley, but I can show you. It would be, oh dear, that got me. Anyway, it'd be like as if I just let go of this and it fell down, because there's nothing counteracting or balancing out. So this one, it would of course slow down, so M2 accelerates down. Hopefully, you would say, if something is just falling with no other forces acting on it, only the force of gravity, we would say this accelerates down with the acceleration of gravity, G. The other ones, so, and when you take a second, turn to your partner, how do these accelerations compare to G? Is it equal to G, less than G, or more than G for each of these accelerations, B and C? Here, what you should have said is that these two both have an acceleration less than G. So for part D, right, the only force acting on M2 was the force of gravity, so it accelerated with G. If you have a mass for M1, now this is kind of pulling down, which would be pulling up in this case, so it's kind of balancing out, so it has a smaller force on M2 than if there were just gravity, so it would have a less acceleration than the acceleration due to gravity. All right, I want everyone to draw your free body diagram for M1. You can pause while everyone is drawing their free body diagrams. So going through this, so of course both of them have the force of gravity. It specifically told me that mass 2 is greater than mass 1. So when I'm drawing the force of gravity for mass 2, I need to draw that longer to show that this is a greater force of gravity than this one. Now, they're both connected to this one string, so they're both feeling the force of tension. In both cases, the tension force is going to be pulling up, so providing a force up. But what's different is that the net forces are in different directions. So we said, in most of these cases, that if M2 is greater, then M2 is going to have an acceleration down. M1 is going to have an acceleration up. So I need to make sure that my free body diagrams show that. So if I'm accelerating up right here, that tension force that's pulling up must be greater than the force of gravity. So I need to show that the tension force is greater right here, and I know that because M1 is accelerating up. Now for M2, this is the same tension force right here, but my FG is greater here because it's going to accelerate down, so the bigger force has to be down. So this is tension. These two are the same force. Tension is greater than this force of gravity, but this force of gravity is greater than the tension. And if you're wondering why it's not two different tensions, it's because this is just one string right here. So there's no way that you can pull with a greater force here than right here, because it's going to travel throughout the string. It's the same string. All right, we want to find the acceleration of the block. So I want everyone to take a second, write your F net equation for each of these, and then replace what you need to replace. So pause. All right, for the first one, the order in which we do this absolutely matters. Here, this one is accelerating up. T is my greater force. So you should have said that your net force was T minus Fg. Whereas for M2, Fg is my greater force. We always want to do bigger minus smaller so that our net force is in the direction of the acceleration. So here, my net force is going to be Fg minus T. Now, we already know how to replace F net. F net is just Ma, so in this case, that would be M1A. We also know how to replace force of gravity. That's mass times acceleration. Again, mass of M1. This one, same thing. And then now for part F, you are actually plugging in. You've got the two masses, solve for the acceleration. So pause. Everyone should be getting a number for acceleration. So let's talk through this. So I'm plugging into my equation. Mass is 50, G is 10. This one, mass is 80, G is still 10. Here, I need to get rid of this T. This first equation is easier to solve for T, so I added 5 times 10 is 500, so I added that 500 over. T is just 50A plus 500. Now I can substitute that in for T. What I need to be extra careful with is this is minus T, so all of this needs to get subtracted. So I have the 80A, 800, minus 50, and minus 500 because I distributed that minus sign to both terms. Now I'm combining like terms. I would add this 50A over. 80A plus 50A is 130A. And then 800 minus 500 is just 300. Now I would divide the 1/8 or 1/30 over, and you would get an acceleration of, don't have my key in front of me, 2.3 meters per second squared. Everyone take a second, find the tension T in the string, pause. Alright, this one you're just straight plugging in. You already know the tension is 58 plus 500. You just found the acceleration, so you plug in, you get your tension force is 615.38 newtons. We could always go through and check. So for this one, right, we got that the force of gravity, we said this was 50, would be 500, and then a tension force of 615. This tension force is 615. This force of gravity is 800. So this one, right, I get a net force that is up. This one, I get a net force that is down. If I subtracted it to get my net forces and divide it by the masses, I should get this acceleration. So that's good. Now I want to get an expression for acceleration, but now I just want to leave my answer in terms of the M1 and the M2. So instead of plugging in the 50 and the A, how would I get my 80? How would I get my acceleration? So I still can use these equations because they're still valid. And now you're trying to solve for A. So hopefully you're thinking through substitution, talking about what variable you might substitute and to get A by itself. So everyone pause, you should be working on that. At this point, what you should have done is taken your first equation, solved it for t. Once you have t by itself, now I can replace this t. Again, be extra careful. When you are subtracting t, you are subtracting both of these terms, so they both get a minus sign. Now we are trying to get a by itself. A lot of you are going to be tempted to divide m2 over to get a by itself. Turn to your partner, tell your partner why that is not allowed here. Hopefully you said because you can't have A equals and then also have A in your answer, so that means I'm going to need to move this term over. So in this case, I would just add this term over, so this would become M1A plus M2A equals M2G minus M1G. Everyone tell your partner what you think you're going to do next. Hopefully you said factor out an A. So if I pull out an A, I'd be left with M1 plus M2. And then last step, tell your partner the last step. Hopefully your partner said divide this whole term over, M1 plus M2. So this is our expression for our acceleration when M2 is greater than M1. So let's always stop and think, like, does this make sense? So here, M2G minus M1G. So does the difference of the forces make sense that this would determine the acceleration? So let's look. If they're the same mass, so if M1 and M2 are the same mass, if they're the same, when you subtract them, what will you get? 0, which we said if they're the same, forces would be balanced. You would have a net force of 0, you'd have 0 acceleration. So that totally makes sense. In this part that we should have subtracting, because if they're equal to each other, you get 0, makes sense. If M2 is only slightly larger, then I have an acceleration, but not a big acceleration. So let's look. If M2 is slightly larger, right, see how when you subtract, if it's only a little bit bigger, you have a small numerator, so you'd have a small acceleration. Now, if you have a much larger, if M2 is much greater than M1, if this is much bigger, then the difference between them will be much greater, so you'll have a greater acceleration. And then it definitely makes sense you're dividing by both masses because this is like your net force, right? So this force of gravity, but minus, counteracted by this force of gravity. And then, of course, you're accelerating both masses, so you got to divide by the both masses. Now, same idea, but now it says that M1 is greater than M2. So I want everyone, if M1 and M2, still the pulley thing, right? M1, M2 on a pulley, but now M1 and M2 are greater. So I want everyone draw your free body diagram for these two and write your net force equation. So pause. For our free body diagram, I definitely have force of gravity pulling down, and I still have tension pulling up on both of these guys. What's different now is that M1 is greater. So for M1, I have the greater force of gravity. So if this is the bigger mass, this guy will accelerate down, and this guy will accelerate up, which means tension is greater than this force of gravity, but this force of gravity is greater than this tension. And this is the same string, so it's the same tension T. Now, once we have these, easy to write our net force equation, bigger force minus smaller, so Fg minus tension for the first guy, and tension minus Fg for the second guy. Now go through and replace, and you are solving for acceleration again. So finish off this one, pause. So here, we replaced F nav with MA, and replaced FG with FG, and paying attention, this one was M1, this one was M2. Needed to get rid of that variable T, so I solved the second equation for T, substituted in, careful with the subtraction, this would be minus both terms. Here, I'm trying to get my acceleration on it by itself, so I need to move this term over. Move this term over. These two both have an A, so I'm going to factor out an A. That leaves me with M1 plus M2. Divide that term over, and this is our expression for the acceleration. You should notice this is super similar to the one on the front. So go ahead, flip over, tell your partner what's different about this one. Hopefully you said in this case, right, instead of M2G minus M1G, you've got M1G minus M2G. That definitely makes sense here because I want my acceleration to be in the direction of the greater mass. So this one is going to be accelerating this one minus this one. The bigger force minus the smaller force here. Alright, in this particular case, I want you to think through. If you were to increase M1, what would happen to the acceleration? Increase, decrease, or stay the same? So this is kind of difficult to do with the equation. It's possible, but I want you to think through like the setup, right? So if you have these two and their M1 is greater and M2, if you were to increase this mass, would the acceleration be more or less or the same from before? Talk with your partner. So hopefully, again, you weren't thinking so much about the equation, just thinking about if you were to increase this mass, if you were making the heavier object heavier, then now you would have a greater force pulling this down than before. So this object would have a greater net force, which is in the direction of the acceleration, so it would have a greater acceleration. So your acceleration would increase. Lots of ways to explain it. I explained it conceptually because the equation, which I'll talk about, is a little bit more complicated. So here, right, if you were to just look at this guy's free body diagram, if M1 would now have a greater force of gravity, so if it has a greater force of gravity right here, and the tension will change, but overall it has more force pulling it down, now it's going to have a greater net force. So it'll have a greater F net, which means a greater acceleration. Now what's tricky about using our equation for just like direct or indirect relationship is I actually have M1 in both of these, right? So I have M1 on the top and I have M1 on the bottom. If you were to increase this, right, the top gets bigger. If you were to increase this, the denominator gets bigger. That means bigger, this means smaller.